Okay, everybody, let's take a look at some of the data I've collected over the years as I've done this experiment in class. First up are the blue dice. Now, let me just explain a little bit. There's some weird mathematical notation here, but I'll explain it and then I'll explain why I did it in a second. The sample means. So when you ran your experiment in the homework for yesterday, you rolled your dice 4 times and then averaged those 4 to get a sample mean. And that sample mean was most likely some kind of a decimal, like 2.5 or 7.25 or something like that. It's too annoying to graph them individually, like 2.25, 2.5, 2.75, and so on. So what I did, I graphed them in little regions like this. So the first region starts at 2 and goes up to but doesn't include 3. The next region starts at 3 and goes up to but doesn't include 4, and so forth and so on and so forth. So in other words, in this particular set of data, there were 2 occurrences over the time I've done this experiment where the average sample means came in between 2 and 3. There was 1 between 3 and 4, 20 between 4 and 5, and so forth and so on and so forth. Okay? Now, the tricky part about this is actually visualizing that. So I've included also a histogram here. Now take a look at that. Do you remember what the original blue population distribution looked like? How does that compare to our sampling distribution? Let's shove it over here in the corner here. Now you notice that the original distribution was skewed. You've got those weird kind of fingers over there on the right. So the first thing I notice is when I sample from that population, I get this graph down here. And just as a reminder from your homework last time, this graph down here is called a sampling distribution. It's a histogram, and also the distribution up top is also a sampling distribution. One is a graphical form and one is a t-table form. But they are distributions of averages that are gotten from samples. As such, they're super useful for statisticians because remember, this graph up here is the population, which we don't, let's take it away. We don't get to see it. Now here's what's cool about this sampling distribution. If I take the average of this distribution to the left, and then I take the standard deviation of that distribution to the left, and just FYI, that's called the standard error, also known as the standard error of the mean, and sometimes just called SE. If you've ever read statistical journals, you'll see SE or SEM for standard error of the mean. Basically, it's a fancy phrase that means it's the standard deviation of the sampling distribution. So if you run the data in this distribution through the Excel calculator, you'll get these values right here. Now I want you to look at those, and I want you to look at what actually happens in the population. I know I just took the graph away and said, you don't get to see this, but you know what? I can't help it. Because look, the average of all of those sample averages comes out to be exactly the same thing as mu to 2 decimals. And the standard error is actually less than the standard deviation of the population. Now that's pretty freaking cool. And what's rad is, it doesn't matter which distribution we look at. Let's take a look at our next distribution. Now this was the next one I did. It's the yellow skewed right dice. This distribution has an average of 4.5 and a standard deviation of about 2.22. I mean, those numbers you would never know anyway, right? Because they're the population values. They're the parameter values. But the average, I call this skewed right because the average is pretty far right of where the spike in the distribution is. Okay, so far so good. Here is the data I've collected over the years. And you can tell right away. Look at where the spike in the samples are. If you're having a hard time seeing it, here's a graph of it. Now, in the original distribution, the spike was further to the left, but repeated sampling allows us to get the spike closer to where the average is. As a matter of fact, if I take the average of all of those samples that I drew over the past however many years I've done this, I come up with 4.57. In case you forgot, the actual average was 4.5. That's pretty close. And once again, the standard error, in other words, the standard deviation of the sample means, is less than the population standard deviation. Let's keep going. This one clearly got an average of 7. It's completely symmetric, but unlike normal dice, right? Unlike normal dice, it's got, I don't even know how to describe this thing. It's like 1.5 modal. I don't even know what to call it. Regardless, it's got an average of 7 and it's got a pretty wide standard deviation. What happens when we sample from it? That's the data I've collected over the years. That's the graph of that data. Now compare that to the population distribution. Isn't that amazing? The population distribution, yes, has a spike at 7. But it also has these crazy gaps down here and then these fat tails. The tails have begun to disappear. That's the summary stats from our sampling distribution. That's the population stats. Once again, the average we're getting is really close to the population average, and the standard error is less than the population standard deviation. Couple more. The orange, this is such a weird one. Definitely bimodal. It's got these two spikes, 4 and 9, with an average of 7. Well, if I sample repeatedly from this population, look what I get. I get this. And what's so rad about this sampling distribution is the bell. Even in spite of the fact the original distribution was bimodal, we get a bell. Ha! The average of all those samples almost exactly targets what the average is. And once again, the standard error is much less than the population standard deviation. Hopefully you're seeing a bit of a pattern here. Okay, one last set of dice here. If you got the red dice, these were actually symmetric in distribution. I called it shifted right because where a traditional set of dice is centered on 7, this is actually centered over on 9.2. So it's got a much higher average than normal dice. And since it's shifted right, but still maxes out at 12, it's got a pretty small standard deviation, only 1.5, about half of what normal dice would be. So you could maybe predict that when I start sampling from this, the data is going to be clustered around that average, and look, it is. And here's a visual of it. And comparing this again to the original distribution, you can just see it's just tightened up quite a bit. So this one probably isn't a surprise to you that the average that we get is really close to the average in the population. But again, once again, we get a standard error. Remember what that is. It's the standard deviation of the sampling distribution. That is less than the standard deviation in the actual population. Okay, let's recap all the kind of cool stuff we saw here.